Okay, welcome back to week one, workshop 1 of week 8. So we're here at workshop 1 of week 8, and we're looking to consolidate the final bit of our intro to differentiation, and we're going to do that today. Alright, so what I wanted to do was just finish off this section here because we've done a lot on the chain rule. Chain rule has been filled up in the tutes, so please make sure you get through all of that because it is very important what we do there. Alright, so what we've got here are logarithmic functions and exponential functions. And so what we often get is, we've done a few of these, haven't we? If y is this function, ln of x, so the ln of x kind of looks like this, doesn't it? Maybe not quite like that. Try again, shall I? So the ln of x looks like this. And it goes something like that, doesn't it? It's the inverse. So that's the ln of x. And yes, it's got all that e of x up, but I don't want to do that. And then essentially what we do is we look at the intuitive little ones like this. Little linears. And then what's happening is the linears start off. They come down like this. They're asymptotic with both y and. So that's 1 over x. There's another part there, isn't it? 1 over x. So that's the 1 over x for the ln of x. E to the x is the one we love. Y equals the log of a to the x. Why would it sum a for sum a? So this is the more general case. So for the more general case, what we're looking to do is see that we've got an answer for not just those things that we've been looking into, but a more general case. So if we get a log and we see that log a is not going to cut it in a general case, so a log a implies it's not log e or 10. So what we do is we take the change of base formula. And why do we use ln? Because it's convenient and we can. And so it'll be the ln of x over ln a. Now the ln of a is constant. Okay, so the derivative will just be the ln of x, which is 1 over x, and the constant stays. The constant stays. So we're going to get 1 over that x ln of a. There it is. Okay, so that's fairly straightforward. Now this one's a bit harder. This is the general case. I'm wondering if you've got your thinking caps on here because this one's a little bit tricky. Don't want to overemphasize this too much, but we've got the skills, haven't we? We've got undo in our favour. So undo will help us out here. We want an equivalent for this. What's an equivalent that we can have? What's an equivalent that we can have for this particular one? Okay, so how do we make this be multiplied by 1? Okay, y equals 1 times a to the x. Still a to the x. Look, I know we could do those kinds of things, but that's not really going to help us out. Okay, what about our ln idea? What about if we multiply, if we take our e to the ln idea? So we're just talking about a to the x. We're not doing both sides, we're just talking about a to the x. Okay, so I'm just going to clarify. We're just dealing with a to the x by itself. An expression analysis. Analysis. We wouldn't spend too much time in analysis, but it does come up. So a to the x. Is it not possible to write a to the x as e to the ln a to the x? I think it is. I think that is undo, isn't it? In any normal territory, we would see that as undo. I've got to putting bubbles around that because some students felt that was easier to recognise as a 1. So 1 times a to the x, 1 times a to the x. Okay, so is a to the x, which is up here. So it's exactly identical to this. So that's a neat way. Now this is a bit more of an advanced gymnastics, I accept that, but nevertheless, what a great way to deal with this. Because what that means is that if we can rewrite this using this idea here, e to the ln a x, what we can do is use our log laws and pull this down here, and so we'll get e to the x ln a of x. So there you go. That's now ready for differentiation. So how would we go about differentiating that? Well, this is a u substitution. So we would have to let u equal x times the ln of a and then we could rewrite this as y equals e to the u. And so we would get two things. We would get dy du, and we would chain that together with du dx. That's our usual procedure for chain rules. Now this one over here is a little bit complicated because it's a product, isn't it? It's a product in this part here. So we're going to go ahead and treat that like a product. So that would be y dash, and of course what that means is that y dash would be equal to u and v. So y dash would be equal to plus u v dash u. Not coming out the way I wanted it to. Okay, so u dash is going to be straightforward. U dash will be 1. That's easy. And what about v dash? What about the ln of ax? So the ln of ax, v dash, is going to require us to do a bit of extra work, isn't it? I want to keep it on the page. So v dash will be dv dx, and we can let u equal, let m equal, because we're going to use the chain rule. Okay, so straight away I've pictured something that I'm going to leave it in the video. Now I'm doing this deliberately because this was getting very complicated, and I wondered why it was getting very complicated. And when I wrote this down here, I made an error, and I'm wondering if you can pick the error. What did I do here to here? Look at this. The x comes out the front. Oh dear, Jason, you did it again. Okay, so we can do the differential for u. So we can let u equal x ln of a, and we can even do du dx. So that makes it a bit easier. And du dx, it's just a constant. If it's 6x, we'd be left with 6. So we're just left with, now we're going to chain this up. So y would be equal e to the u, and so dy du would be equal to e to the u. Calculus is not the problem. Look at the silly little transposition mistake I made. I left the x there. I didn't move it. In the log law, what a silly thing to do. But anyway, I'm glad I've done that, because we're going to chain these together. Okay, and so those terms will become y dash. So y dash will become e to the x ln a, that's that bit, times the ln of a, that's the other part of the chain. So I'm all of a sudden very impressed with myself. Now look at this, x to the ln of a can be rewritten back the other way, And what we're going to end up with is a substitution. Well, there's our substitution for AX. So in actual fact, we're going to substitute that for a to the x. So that's our differential. Okay. So I'm sorry about that little bit of a rigmarole, but I'm glad I did that because it's an easy to do gymnastics. It's nothing to do with calculus. A to the x times the ln of a. So that's what we've come out at for the differential of this particular one. So where we've got a general case of an exponential, we're looking to say that we would multiply the ln of a by a to the x, and that would be our final part there. So this one here is a match for this one. Okay, y dash. So the development of that a little bit tricky, using this substitution, using a u, putting all the steps in, chaining them together, and you get your final result. Now this part here, this substituting of previously made, I'll use like a movie colour. So this idea here is a bit more of a thing that people get involved in maths. Okay, so we don't want to overemphasize it, and then putting it back into the final answer. So I'm just kind of highlighting that with the circles there, suggesting that, it is something that we need to be aware of that does happen. All right, let's keep going with that one. So we've got some examples that we can do. We can differentiate the following. So we've got y equals the ln of x. So we can let u equal 3x. And by Leibniz notation, du dx is equal to 3. We rewrite this in terms of the ln of u. And so dy du, there's our chain, is 1 over u. Okay, we can put our chain together by putting the expressions together. So y dash will become dy dx. I'll just do it the once. Dy through something else. And the something else we've worked out is du. And so that always applies. And if you get used to doing that, when you come time to build physics problems or real world problems that have rates in them, this is a really easy task then, because you become a little bit skilled in the whole area. Okay, so 1 over u times 3 is equal to 3 over u itself was 3x. Unexpected, they cancel, and so we end up with 1 over x. Okay, sometimes you can have a go at doing a change to a log law version, okay, and in that case there you would recognize that the ln of 3x is a product, and so that can become the ln of 3 plus the ln of x. So the ln of 3 is a constant, so that becomes 0. And then the ln of x is 1 over x. So the total is 1 over x, which is the same. Okay, so that's just an alternative way. Sometimes it's convenient to introduce the log laws. In that case, it made no difference to the difficulty of the problem, but we need to keep that in mind. Also, we could do the same thing here. We can take the ln, we can take that 3 and put it out the front. So if I were to just maintain that pen colour for a minute, what was that one, wasn't it? So we would have this as pre-work. Now you don't need to do this way, the ln of x. So it's just a product 6. So if we go and do y dash, the 3 will remain because it's a product, and the ln is 1 over x, so it'll be 3 over x. Now that's one way of doing it. You can see that's got some merit in it. Okay. Also though, my preference is that you develop your chain rule. Okay. So for y equals the ln of x cubed, let u equal x3. So du dx. And then we can run back here and write y equals the ln of u, and then we can do dy to u. And there's our chain. There's our chain. We're going to put those together. So the ln of u is 1 over u. The du dx of this is 3x squared. Put the chain together. And so y dash is equal to 3x squared over x cubed. And you can clearly see that's 3 over x, which is the same value. Okay, now going the long way, we could have put, I know, don't like me doing that. Could have done that. It's the same. Okay, so it's the same answer. So either way is fine. All right, this one here. Now this is rewritten in this nomenclature. I don't like seeing these terms. I don't mind it for trig so much, but I don't like seeing these this way because it's just not taught at school that way. So that's what that means. So we're going to deal with it this way, that u equal the ln of x. We're going to rewrite y in terms of u. Then with Leibniz, we're going to put our chain together. And that is our dy dx together. So that's going to become 3u squared. This is going to become 1 over x. We put the two together as a chain, and y dash becomes 3 bracket squared over x, and u was the ln of x. So that would be my preferred form of that particular answer in that way. All right, so just a couple of others to do, and we'll just keep going here. And I might pause there and come back for a new video. Back soon.